Swayam Prabha. Digital India. Educated India.
So this session I'll bit of graph theory, graph based data analytics on. So whatever you learn in your graph theory course, data analytics, I try to recall it, and then few centrality measures which is required for a data science on. Okay, how many of them have formally studied a graph theory as a course? Most of them, others have studied a part of a discrete math. Okay. So what are the things you know as a graph? Why the graph is important for data science? Yeah, this is more interactive. I don't want to take it in a monotonous way. Provides a dynamism. Good. Why a graph theory is required for a data science? It deals a dynamism. Okay, that good. And so we should visualize the data. Then helps us to find the relation between the data. Okay.
Certain real world problems can be modeled as well.
Yeah. Real world problem can be modeled. We'll see. We are going to see some case studies on that. Okay. Any other? We missed the major part. The second one. You can do an analytics on data analytics on. Okay. So far, if you are given a data, probably you want to predict something. For example, if you are given a data of 10 years rainfall data in Coimbatore, you may able to predict, okay, what is the rainfall in 2023, 2024 using some statistical analysis. When you have a data, probably using statistics, you may able to that. Okay. Recently, researchers start thinking on a graph based data analytics on that. Okay. So basically, you can extract certain futures, okay, based on the graph model. So very powerful on. There are good merits are there. There are a few demerits which I explain it later on. This as he says that this all a few examples on that. You can model real world problems into a graphs on that. Okay, real world problems either in a biomedical engineering or comes from a medical data or from a data coming from a stock market, data coming from a business or transport network. Okay, any real time data probably you can convert into a graph. Okay, with a suitable labeling of vertices and connections between the vertices, we may be able to model. Then you probably can predict it on that. Why we want to predict it? Because you want to extract certain futures on that, and then you have to go with some decision on. After taking some future decision, then we will go for a decision. There are various graph parameters are there. If you look into the graph, probably those who are studied as a graph theory, it's a full course. There are different parameters in terms of that. For example, domination number is a one very important parameter on. Okay, anybody knows what is a domination number? What is a dominating set? Maybe those who have studied a graph. Very powerful parameter which we have not deal here. I just it is for a given a set of network, you try to find few hotspots. These hotspots will dominate the entire network on that. Okay, that means set of vertices which dominate the entire network. So based on that, there are variations, lot of variation in the domination. Okay, domination, that's something called connector domination, inverse domination, pseudo domination, things like that. Then based on that, dominating numbers are defined on that. Okay, so one of them. Then there's something called independent number. This probably some of them. Anybody know? I'm just highlighting on. Independent number is something like you try to choose the vertices which are all independent. Okay, so we can define it on that. Then some matching number already Professor Venkatesh has introduced it. What is a matching? Maximal matching and perfect matching. Am I correct? Then probably you can study a graph parameter. Matching number is a one graph parameter. Then there is something called the covering number. There are other parameters like an eccentricity based on the distance, okay, and then detour distance is there. Anybody has heard about this? Detour, this is a distance parameter based on the maximum length on. Usually when you talk about the distance, you always talk about the minimum. This talks about the maximum on that. So, there are different variation in detour distance, and detour distance also used to analyze certain networks on. Okay. Eccentricity is one of the important one for a network analysis. Other than that, there are different graph indices are there. Okay. It's like a Wiener index, Hosea index, PA index, C's index, and these are all the different parameters. These parameters are invariant parameters on that. Okay. That means if you take a graph with the isomorphic, probably you will get the same index on that. Okay. This is all very powerful on that. This has applications in real time applications in communication engineering, data science, particularly on chemical graph theory is a lot of real time. Okay. To analyze this molecular structures, probably you may require this indices on that. Okay. Some of them gives energy number, some of them gives a domination number and valency number and things like that. And there are other parameters, is as a chromatic number. This is also a familiar one. What is the chromatic number? Chromatic number of a graph? Pardon? Minimum number of colors required to properly color the vertices on. Okay, so there's a lot of variations on that. There's a relation between the chromatic number and this independent number. Okay. Then there's something called a burning number of that. This you can do it, take a graph and sequentially you burn this vertices and then you can find it on that. Probably anybody knows, I think. Yeah, he knows that he's working on burning number of that. Then there's something called connectivity number. This also we have discussed what is mean by a one connected graph and two connected graphs. I think Professor VR has introduced it. Am I correct? So, apart from that, there are few more parameters are there. That's one parameter we are going to discuss it here. Is this more important for a data science or data analytics or data network is we called as a graph centralities. Okay, this is what. Anybody heard about that? What is a graph centrality? Maybe, yeah. Good. Yeah. Any other? Okay, it's a very important one. See, suppose you have a given network. Okay, as I told, any data probably you can visualize as a graph. Okay, once you visualize it, then probably you can identify that which are the nodes are very important nodes or very important parameters on that. Probably you can extract it on. Okay, maybe the future selections can be done using these centralities on. So, centrality is a measures like the measures of this. You have a different parameters on that. So, you can centrality you can it's a one parameter which you can from that you try to extract which nodes are important in a graph on. Okay. So, there are different centralities are there. So, we are going to define what is centrality measures, some examples. And then something that if this what is the community direction, this is one important one, then probably 2-3 case studies which two of them are interested to show it on. Okay, let us see the last one. The second part is probably after the break we will discuss it. This is what. Okay, this is a famous Twitter graph. Anybody has seen your Twitter graph on that? How many of them are in a Twitter? Oh, you have seen your Twitter graph? It's beauty. Maybe you just go to a API, graph API in a Twitter API, and then probably you can extract it on that. It's very interesting. Where the nodes are, those nodes are these IDs, and then two IDs are shared by our tweet is a okay. Then there is an H on that. They have different ways on you can tweet it on that. This is a Facebook graph similar to the. I know that very few people are using Facebook, so it's a Facebook graph. It's not a Facebook graph of mine, okay, because I don't have an account in Facebook or Twitter. This is a Facebook graph, probably which you can extract this. You heard about this graph API? Yes, sir. Yeah, this is a way you can do it, just using a graph API. You can extract the Facebook network on that, or Twitter network. Mostly any social media network can be extracted. You can visualize it using this. Okay, this is a one you can try it on that. They may not give all the details, probably certain details they will give it in a free of cost. So, there are few parameters which are going to discuss it. These are the few things on what is the degree, closeness, betweenness, click and things like that. Okay, if you look into this graph, okay, when I say a graph, probably you can correlate as a network which comes from a data on, okay. Which is most important one? H. Any other? This H. Okay, why? Pardon? Okay, you just cut it, just remove this H, probably the graph is disconnected, that's fine. Any other one? Vertex E. Okay, this one, why? Pardon? Increase the distance of shortest path. Let us see. Okay. Then? Now, which node? E. Okay. Okay. So, E is, so for in terms of your parameter, E is the most important one. Any other? I am saying that this M or this I is also important. Why? Any other guess or any other? See, these are all important for various reasons. Okay, this is important because of it's the betweenness. You just, if you cut this, then it's disconnected to the two graphs on that. Okay, in terms of betweenness on that, we'll explain what is the betweenness on that. In terms of a closeness, this is. In terms of, as she says that, in terms of you look into the degree, and this is important. In terms of if you look into this important, or probably in my logic, this is the most important one. Shall explain why it is important. Okay. So, these are the few parameters. I am just giving only an idea, because this is a big one on that. You have a graph analytics is a big topic on that. We can offer as a full course. I used to offer a course for a BTech, MTech and PhD integrated MSc on different levels on that. Okay. So, talking in 1 hour, 1.5 hours is impossible, but still can try. Okay. So, what is a centrality? As I told, centrality is a measure which you can extract it from the graph network on that, and different type of centralities are there. These centralities are most important one, or they are invariant on that. Okay, invariant properties on that. So, it means that you even if you have a same graph with a different isomorphism, probably you will get the same parameters. So, this based on this, probably you can extract certain features or parameters or certain properties of the graph, and then you can predict it, and then you come to the conclusion on that way. So, you have a data, visualize the data as a graph, we are going to do that, and that applies certain centralities based on the requirement on. You can try to extract it certain features, based on that probably you can predict it, then you can act it on it. So, it's a cycle on that. So, you have a data, then model it, then you apply certain centralities or graph algorithm, make a predictions, then take a decisions, then apply to the model. It's things like that on. Okay, it's a learning on that. Okay, like different learning models. Okay, so there are different centralities are there. As I told, this has a lot of applications in network and things like that. So most of the centralities is either degree based or a distance based on that. So, what is the degree? Degree of a vertex? Number of? Good. Number of edges is. So, what you know about the degree? Suppose I am giving a graph. So, what can you say about the degree? Sum of? Okay. Sum of degree over all the vertices is? Okay. 2e. That is good. Any other one? There are a lot of things you can see. Okay, I am talking about that undirected graph. We will come to the directed. Directed graph is directed graph. You have an in degree is there. You have an in degree sum and out degree sum. Similar consequence. Any other one? Vertex 1 with degree 1 is called pendant vertices. How many pendant vertices in a tree? How many pendant vertices in a tree? I hope everyone. Tree is a connected acyclic graph. My question is how many pendant vertices in a tree? Partial answer is here, but I want to know exact answer. How many pendant vertices? Okay. I have a tree like this. How many pendant vertices you have? How many pendant vertices? You call the leaf nodes in terms of a computer science term. 5. Okay. How many pendant vertices? Okay. Tell me how many pendant vertices in a tree? Is it at least 2 or at most 2? Yeah, you have a pendant vertex. Can I have a tree with only one pendant vertex? Why? Can I have a tree with only one pendant vertex? Yes? No. Number of degrees? Number of edges is always integer. Which property? Okay. No. You have, see, for example, I just put, see here you have, of course, this is not a tree. I have a graph with one pendant vertex. It will form a cycle. It will form a cycle on. Okay, so lot of things you can talk about that. Okay, there are one more important property on degree. I try to extract it on. Let us do something on the degree so that you will wake up on. Okay, so now I have a graph with the degree sequence like this: 1, 2, 3. A graph with the n vertices. Can I have a degree sequence is a graph with one vertex of degree 1, one vertex of, that means all the degrees are distinct. Can I have a graph where vertices are distinct degrees? Is it possible? I just interact it. This is just for interaction. I don't want to take it. Take a graph, one vertex of degree 1, one vertex of degree 2, one vertex of degree 3, one vertex of degree 4, and so on. If you have a 10 vertices, then the 10th vertex of degree 10. Is it possible? I don't know. Anybody? Somebody says that how? Yes, it's possible. No, it's a simple graph. There is no self loop and parallel edges. Okay, can I draw? I just make simplify. Can I draw a graph with the vertex degree 1, degree 2, 3, 4, and 5? How many vertices required? There are 5 vertices on that. it is a simple graph. It means there is no parallel edges or self loop on that. Can I have a vertex of degree 5 with 5 vertices? Is it possible? I am repeating, you have a graph with 5 vertices. Can I have a vertex of degree 5? What is mean by degree? It's the number of neighbors on that. Am I correct? A degree of a vertex, I say degree of a vertex is 6 means there are 6 neighbors on. Am I correct? That is the meaning. So, for example, degree of this vertex is 2 because there are 2 neighbors on that. So, can I have a graph with 5 vertices where one vertex is degree 5? It is not possible. So, this case is ruled out. It means this vertex must have at least one degree which is from 1 to n, okay, something like it may be 1 or 2 or. So, one more interesting property is in a graph at least 2 vertices are same degree, at least 2 vertices are same degree on, okay. Let me have one more example. Can you give a graph where you know what is a regular graph? What is a regular graph? Yeah, regular graph is degree of all the vertices, or I say k, then I say that this graph is k regular. Am I correct? Yes? Okay. Let me. So, now tell me about degree and regularity. Is there anything relation between degree and regularity? I have a k regular graph, okay. Okay, I have a k regular, maybe I take it a 3 regular graph. What do you mean by 3 regular graph? Sorry. What do you mean by a 3 regular graph? Degree of all the vertices are 3. Am I correct? Okay. So, I say 3 regular graph with n vertices. Can you guess what is n? Just guess it. Is it n is multiple of 3? Can it be n is multiple of 3? 6, 9, 12, things like that. Say yes or no, I just want to your guess. I am asking, is it n is multiple of 3? Yes or no? My graph is a 3 regular graph. Can you have the number of vertices is multiple of 3? Need not be. Okay, then what is the answer? N must be? N must be even. Okay, good. This n must be even on that. Okay, that means you haven't. See, that means you cannot have, because this property is used regularly under centrality measures. When you find a centralities, particularly on degree centrality, they apply this logics on that. Okay, to extract certain features, they use this degree properties on. That means you cannot have a graph with odd number of vertices with odd regular graph. Suppose I am asking to construct a 3 regular graph with 7 vertices. You have a graph with 7 vertices, like you have A, B, C, D, E, F, G. Is it possible to construct it with 3 regular? Answer is no. Okay, there are a few things which is okay. It's fine. Okay, what else you know about degree? Probably you can talk 1 hour for a degree. Such a beautiful concept on that. Because most of the centralities are degree based one, few of them are distance based one. What are the things you know? The elementary, I am not talking about the bigger one. I am giving a connector graph G is connected, okay. what is the degree of can you tell at least some lower bound? Sorry. Degree must be at least this. No, degree of this is degree of a vertex. I am giving a connector graph. Can you say that the degree is at least this? N minus 1. No. If you take a path, it may not be n minus 1. At least 1. If you take a graph like this, you have a 2. This is a disconnected graph. Degree is at least 1. N by 2. Is it n by 2? I don't know. Just think on. Okay, what will be this? This upper bound is easy. Upper bound is of course worst case n minus 1. As I say, simple graph, you don't have parallel edges or self loops, it is n minus 1. So, this of course, this is n minus 1. So, probably you just look into this part, okay. This is today's your homework on that. Maybe think what is the degree requirement for a connector graph on that, okay. It is not. The other way also, you see it is like this way. Suppose you have a graph G is connected, then this, what is the word? The other way also, other way also you take it, suppose some k is less than or equal to degree of the vertex for then G is connected. So, what is a k? These things you can do that, okay. That means if a graph with at least this degree, okay, degree of the every vertex is at least this, then the graph you can guarantee that this graph is connected on. So, you can talk about once you talk about the connectedness, then you can talk about the different parameters and things like that, okay. So, it's all interesting on connectedness, sorry, degree on that, okay. Anything, any discussion or any clarifications, suggestions? Okay, let us move to this. Before going to the centrality, let us move to something on a distance. Okay, so distance I talk about that. So, what do you know about the distance? What do you know about? Suppose I have a graph G, I have a vertex U and vertex V, and this is. So, I'm say that distance between U and V is 5. It means just warm. What do you mean by that? Length of the shortest path on that. Okay, so it's the length of the shortest path on the length of the longest path, which we call the detour, and detour distance is a separate on. So, for a given graph, okay, now I want to find a shortest path on that, length of the shortest path. So, how to find it? What is the algorithm? That is a very famous algorithm. I hope everyone studied, even those who have studied a discrete maths probably. Dijkstra's, okay. Dijkstra's shortest path algorithm, okay. This is a very powerful algorithm. Dijkstra itself has improved this algorithm several times, and then it's a very one of the powerful algorithm used in many applications and things like that. Okay. Anybody knows how this algorithm works? Just beat on. Okay, this is a simple logic. You take a vertex U and another vertex. Suppose there is an H. Okay, it's based on the labeling, or you call, I don't know how it is. Suppose you have, this is a label of U, this is label of V, and this is weight between U and V. If L of u plus weight between u comma v is greater than or equal to L of u. Okay, maybe I'll take it less than, then it may be easy. Less than or equal to or less than. Okay, then yeah, then your L of u, sorry, L of v. I am not going to the algorithmic part of this. This is what is there. That means, see, you just find it. This is your u and this is your v. Now you have a weight on that. Okay, so the labeling of this plus this weight is it is smaller than the label of this. Then you replace this label by this. Okay, that's the logic on it. Okay, so this the logic is, suppose I am reaching. See, I am reaching some places. I am reaching here. This is by 10 hours and this takes some 2 hours on. This is a 10 hours. This is 2 hours, but this I am reaching something like some 20 hours on. So reaching this reaching the node V is better by 10 plus 2 on that. So you change the label on it. Okay, this is a logic and general logic. So very powerful algorithm. Everybody knows what is the complexity, because this algorithm we are going to use it for measuring the distance based centrality. What is that? Log of V plus E. You should know. Basically, this is n square. In general, it's n is a number of nodes. Maybe if you apply some specific data structures, like you have a heap sorting or some specific sorting, probably it may convert into order of E log n. E is a number of edges and n is a number of vertices on it. Okay, this you can this is very depend on what type of data structure you use and what type of a sorting method you use it on that. It depend on that. Okay, so this about that. So this Dijkstra's algorithm basically find a shortest path between two vertices. It gives a shortest path as well as the shortest distance from one vertex to other vertices. That's the other algorithm. It gives a shortest distance between any two nodes. No. Those are studied. I think it's there in discrete maths also. You heard about Washer's algorithm? Washer's algorithm. This is another algorithm that runs on order of n cube. Of course, you can change the data structure also to reduce its complexity. So basically, we use Dijkstra's algorithm or Washer's algorithm for finding the distance between two nodes in this one. Okay, with this fundamental, probably we will move to the some centralities. There is a one disadvantage in a Dijkstra's shortest path algorithm, which cannot be used as here. Yeah, it cannot be applied to a negative weights on that. If you have, for example, you have a data where two datas are between two datas, you assume some negative weights on that. Some, for example, some loss or something like that, some depreciation loss, something. If you assume as a weight, then Dijkstra's algorithm will not work on that. For example, I am traveling different places, one place to another place, and things like that. My weights between the two nodes, I assume that it's a loss. If I travel by this, it's a loss for me. Then you cannot apply the shortest path algorithm. It never apply on. That's a big problem. But there are modifications of this Dijkstra's algorithm with negative weights are there. Probably it's all in the literature. Okay, so let us go. There are few centralities are there, which I am going to do a few things on that. Okay, among this degree centrality, closeness centrality, and things like that. So degree centrality is basically you just try to extract the degree of all the vertices, all the nodes in a graph. You take it one by one. Okay, just list out on the degree centrality. and then take the average on them. Okay, this way. Okay, this slides and this talk will be there in your. Okay, I'll share it, okay, along with the other one. So you don't require to write it on. So for in the case of a direct graph, I say that you have something called in degree centrality and out degree centrality. In degree centrality is number of edges incident into that node. Out degree centrality is number of edges going out of the node. Then you can take as an average on. Okay. So for example, if you look into this graph, this node has more degree centrality. Of course, this node, there are different nodes with a different degree centralities on. So the degree centrality of a vertex is just find the degree of the vertex. It is nothing but just sum. You take an adjacency matrix, then you just add the number of ones in the corresponding row. I hope you know what is an adjacency matrix is a matrix where row and column represent the vertices. Okay, if the vertex I is adjacent to the vertex j on that. Okay, so two vertices are adjacent. The corresponding position is 1 in the adjacency matrix. So it is enough to find, or it's enough to sum the rows, then you will get the degree of that vertex. So degree centrality is there. This is a normalized one. Okay, this is a normalized degree centrality for a under graph. For example, if you look into this vertex, the node 3. Node 3 is there, the degree is 3. See here, degree is 3. There are 9 vertices are there, 9 nodes are there. So 3 by n minus 1, that is 3 by 8 is a degree centrality on. Okay. Very powerful centrality. This is an example. So based on the degree centrality, you have a degree is there. This is a ratio. Based on that, probably you can rank the node of that. Suppose you have a large network. The network you find a degree centrality, and then you can rank it on that. So what is this practically this rank tell us? What you can, which future, see you have for example, you have a big network on, assume that there is a road network, a transport network on that. In that you have a degree centrality. What this degree centrality convey to us? Practically. The degree says, please, this degree says is there is a meaning on that. Degree says that there are so many neighbors on that. Okay, how many neighbors for a node? For example, if you look into the transport network for a particular place, how many cities are connected to each other? Okay, if you look into the airline network, okay, where each airport is considered as a node, and then if there is a direct connection between the two airports, for example, Coimbatore and Chennai, Coimbatore, Hyderabad, then there is an H between Coimbatore, Chennai and Coimbatore, at least one flight, direct flight is, then there is an, okay. So you know that, for example, Chennai has degrees some 56. It means there are 56 different airports is directly connected to Chennai. That's the meaning on that. But what this rank says, this is a degree we understand. What is this rank says? See here, the degree is there and then rank is there. Is the rank conveys the same? If the degree is more, the rank is the best rank.
Based on the centrality value, the rank will be given.
I am asking if the degrees are more. That means a node with the maximum degree becomes the highest rank.
Yes.
I am repeating, a node with the highest degree becomes the highest rank. Is it true or not? In general true, particularly first few degrees, the top are there, but when you talk about the middle on that, if for example, if in a case of a cycle, okay, if you look into this cycle graph, what is the degree centrality of the each node? 2, am I correct? What is the average degrees? Suppose I say this is n, number of vertices are n. What is the average degree? 2 by n minus 1 for all the nodes. Am I correct? Degree centrality of the average degree centrality of all the nodes. So can you say anything on the rank? rank are same, all the rank are. In some cases this rank is there, but probably you will get some idea about the rank, and then the equal ranks gives that which are the nodes are in a probably either equal weights in terms of a degree on. Okay. So another powerful degree centrality. This same thing you can apply for a director graph with where you have an in degree, you can have an in degree centrality, and then you can have an out degree centrality on that. Then based on that you can rank it, rank for a in degree, rank for out degree, or you take in degree plus out degree, then you can rank it on. Okay. This is a one interesting point on that for a social network. This degree centralities behaves like this distribution. You heard about this distribution, power law distribution. Those who studied a probability distribution as a separate course, probably you know that. Okay. So this behaves as a power law distribution. Power law distribution is a very famous one on that. So this distribution is very rarely used on that. It's like it's not like another distribution. So this distribution, see if any situations like that, okay, that means things is happen in a normal way, okay, usual way. That means 20% of the things. This is a very famous rule called 80-20. That 20% of the things will be done by 80% of the people, and 80% of the things will be getting on a 20% of the people. It's like that. That means imagine that 80% of the people earn only 20% of the money, whereas 20% of the money is earned by 80% of the people. This other way. Then you can just think of this power law distribution. Okay. The power law distribution is, so what happened, this degree centrality fits to the power law distribution for a large scale network, it is not for a small one. So any network where the degree distribution follows this power law, okay, that network we called as a scale free network. Okay. This is one of the things, those who are interested on the social network, large scale network and things like that, probably you will feel that it's a scale free network. And that's a beautiful book by Professor Barabasi on network science, okay, where he defines all those things on that. Any network is a large scale network is considered to be a scale free. It means that the degree distribution follows this power law. Okay. This is an example of a power law distribution. See, things goes down on that. This is, you have a maximum. Okay, I'll show you in the next. Okay, this is a basic normal distribution. This is a power law distribution where you see many nodes with only a few links. This is basically this is a number of links, and this is a nodes with the k links on that. So if you fit into that, this seems to be a power law distribution on. So most of the large scale network on this. When I say a large scale network with some 10 billion nodes and something like that, you may have this. Okay. It may not be applicable to a node of network with a smaller number of nodes. Okay. This is a one, as I told, this is a science of a network. There is a beautiful book by Barabasi. Maybe you can refer this. These things have explained it well on it. Okay. It's a good book. So the next one is a closeness centrality. This is based on the how these nodes are close, how the one node is close to the other node. See, if you, for example, if you look into this a group of people, how one person is close to all. Okay, if you want to measure the closeness, probably this is a interesting parameter on that. Okay, so this gives one type of a variation. That means one type of a parameter where this talks about the closeness on that. Okay. So closeness is this capital N is a number of nodes in the network divided by this degree, distance or distance between u and v, summation over all the vertices u on that. Take a vertex, this is a closeness centrality of the vertex v. Numerator is a number of vertices minus 1, denominator is you take the distance from v to all the vertices, you sum this distance, that gives this. Okay, this is what we, as I told, this the previous centrality is degree based one, this is the distance based one. Okay, I will just show you an example. This is a beautiful one. For example, if you look into this graph, okay, this is a very standard graph on that. If you look into this node A, if you look into this node A, AB, what is the distance between A and B? 1. AC, I talk about the shortest distance. AD shortest distance to AE 1. So this is sorry, AE is 2. This is a distance matrix on that. Probably using your Flyart-Schwarzschild algorithm, probably you may able to get this one. You just get it. So this can be this matrix, distance matrix can be get it from Flyart's algorithm. So distance from AB is 1, AC is 1, AD is 2, and AE is 3. Now you sum it up. Okay. The sum gives a denominator. The sum gives a denominator. Numerator is, of course, there are 5 vertices. 5 minus 1 by 6. Okay, this is 1. So like that you can do that. Then based on that you can rank the node on. So you can ranking the node. So which node is important in terms of a closeness is there. So which node is a more closeness centrality? See this B. This B is close to A, C, D and E. So this parameter is one of the beautiful parameter in the network on that, in which node which is close to all other node. Okay. If in the case of, for example, in the case of, let us take this. It's like 1, 2. This is a path graph Pn. Anybody can guess what is the closeness centrality of this one node 1, the first node? This the closeness centrality of the node 1. Numerator is simple, n minus 1. Denominator distance between 1 and 2. What is the distance between 1 and 2? 1. Okay, I will write it 1. Distance between 1 and 2, sorry, 1 and 3. 2. Distance between 1 and 3. Sorry, 1 and 2 is 1, 1 and 3 is 2, 1 and 4, 3. So, and so on, plus distance between the first vertex and last vertex. What is the last one? 2 by n. So, what is it? Then you take a summation, you take the summation and put it in the summation, what you will get? 2 by n. Okay, like that probably you may be able to guess it on that. Okay. So, let me have one more example. It's a famous example cycle, sorry, it's a Cn on that. It's like you have 1, 2, 3 and so on n. What is the closeness centrality of any node? Okay, this is, and numerator is n minus 1, denominator distance from 1 and 2, 1, 1 and 3, 2, 1 and 4, 3, okay, think over it. Okay, I'll try to draw in a simple way. Let us take one, 2, 3, 4, 5, 6, 7, 8. This is C8. Now tell me what is the CC of the first vertex? Numerator is 7. Am I correct? N minus, there are denominator. It's a simple calculation, it's simple mental calculation, you don't require. Distance between 1 and 2, 1, 1 and 3, 2. Okay, so 1 plus 2 plus 1 and 4 3, 1 and 5, 1 and 5. Shortest distance, is it 4 or 3? 4. 4? Okay. 1 and 5, 1 and 6, 3, 2, 1. If you sum this, okay, this is not like a path, it is something on that. You just go halfway and then repeat it on that, you will get it on. So, like that you can find it. This centrality is a beautiful centrality, one of the most important one, closest. When you want to identify that which node is more closer than the other nodes with respect to the other nodes on that, this centrality is used on that. Okay. Let us have a, this is this harmonic centrality is just reciprocal of this closeness centrality. It's not exactly, it is similar to that. Okay. You just, this generally we call as a reverse of that. Okay, this is the reverse sum of this one. Okay, this also used to find different measures for a network. Okay, this you can do it a similar way. Then there is then something else other called as a betweenness centrality. Probably the word itself is there, it's a betweenness, and how a node between the other node on. See, for example, it is used on a communication network. Suppose you want to communicate certain things to the others, okay, not by direct, via some other person. Okay. So, now how many ways you can send a message to this person, and then this person, how this person is vulnerable on that. Okay, that means how many messages he is getting, okay, from others, that means he passing through that on that. He is like an intermediate on. So, that measure you can extract it from this betweenness centrality on that. So, this betweenness centrality is the one measure where betweenness centrality of the vertex V is you find the shortest path between S and 3 through this vertex. Okay. Through this vertex you try to find it, that is your numerator. Your denominator is you find the shortest path between S and T, all the shortest path on. Okay. The numerator is via this V, that means how many informations which I have to pass through, this coming message is coming to me and then I try to pass it on that. Other things is how many information is going out on that. It's just this look like this way. Suppose you have a vertex, this is a vertex V, how many shortest paths via this, like this is V, this is your numerator, denominator is a total number of, okay, if you take this is total number of shortest paths between S and T on that, you just vary S and T, you will get it on. This is a beautiful measure. Okay, for example, if you look into this graph, okay. Now, if you look into this vertex 9, okay, which vertex? Vertex 4 is here. Okay, let us look into this vertex 9. Okay, let us look into this vertex 9. How many paths between all the vertices via 9? Shortest path I am talking about. I am just looking this numerator, just numerator on that. Numerator is number of shortest path between any two vertices via this vertex. So, how many shortest paths between any two nodes via 9? 1. Which path? What is a path? You don't have a path, am I correct? You don't have a path on that. It's like you have a corner, so it's a 0. 0 mean that it's something like it's like a leaf node on, okay, or a pendant vertex on that. It's something like that on. Now, for example, if you look into this 4 is here, okay. Probably then now you want to communicate something from this side to this side. Naturally, you have to go via 4 is, am I correct? So, this 4 is the most important node in this aspect on that betweenness on. Okay. So, now I try to take it, how many paths from this group to this group, probably you may guess it. Okay. Can you guess how many paths? Of course, within, for example, the shortest path from 1 to 2, 1 to 3, 1 to 4, sorry, 1 to 2, 1 to 3 and all is not via 4, since it is the shortest path on. Now, I want to find the shortest path between this vertices and this vertices. What is the number? It is given here. This table is given here. From that table, and then you can try to find the you can try to find this value. This value gives the betweenness centrality on that. Okay, we'll show some examples on this. Okay, so the betweenness centrality of this, of course, is here. This is betweenness centrality of the node 9. The same graph is there. Between centrality of this 2. Why is 0? See here. Because this is similar to this. It's not a leaf node, but still, because it's another corner node on that. Okay, it may not be that significant in terms of information exchange or information transfer on that. See here also there, even though the degree is more compared to this, degree is more, but still you have a betweenness is 0. See here also the same degree, this vertex and this vertex. If you look into this vertex or node 5, here the betweenness is 6, okay, the degree is 4. Am I correct? So, this centrality gives certain type of measures or okay parameters for a node on that. When you want to see that which are the nodes are important in terms of the information exchange, then this degree centrality is important on that. Okay. Then probably this is the last one on okay. There are a few more things on that. I just stop it for a break. The eigenvector centralities, that still you have a psi I centralities there, hyper centralities, different centralities are that. In fact, Dr. Arun also told me based on the graph coloring they have a centrality on that. That's called coloring centrality on that. Recently they introduced it and then they obtained for some graph network classifications on that based on Lavos theta functions. Okay. So, there is a lot of centralities and centrality measures are there. This is a one now. This is a very interesting one. This centrality is that you know what is eigenvalue and eigenvector. Am I correct? I hope everyone knows what is an eigenvalue and eigenvector. Yes or no? If you have studied in your semester 1 or 2, something like that. Suppose, okay, I will talk about the matrix A. What is the eigenvalue? Eigenvalue and eigenvector. So, almost definition is here, see here. For a matrix, if you are able to find a lambda and a vector x such that Ax equal to lambda x, then lambda is called eigenvalue and x is called eigenvector. So, how many eigenvalues are there, how many eigenvectors are there, how many linearly independent eigenvectors, okay. These things are a different interesting topics in linear algebra which you can do it on that. So, this eigenvalue centrality is also most important one, okay. This used in different places like a ranking and things like that on that. But what it says that is, of course, computing is little difficult, it is not that easy like others on. This computing is requires some more time, okay. You need some decompositions like SV decompositions, okay. Based on the decomposition you can find this eigenvector centrality. So, eigenvector centrality is defined by this way. You want to find this, okay. Xi, it is 1 by lambda. Lambda is the eigenvalue corresponding to the eigenvector and summation over Aij Xij on that. This is a matrix associated. Based on that, you find the eigenvector centrality. This eigenvector centrality is a one beautiful measure. What is it? No, it gives the best among the best on that. See, suppose I have some 1000 students on that. Now, I want to select some 2, 3 as the best students among the 1000. So, you do some measures and then select some 15 or 20 students in the best one. Okay. So, your teachers, your class advisor, somebody is selecting, okay, these are the 10 students on that. Among that, I want to choose 1 or 2. So, you want to choose best among the best, we need to use this on. Okay. So, very beautiful centrality on that. Okay. Like that, there are different centralities and different measures on that. Okay. I just take 1 or 2 things on. Okay. There is something close clustering centrality. Probably if you have a time, we will do it little later on. Okay. In the next session, probably we will have some demonstration, whatever we based on that. Okay. Okay, there are two things on that. Tomorrow I will try to continue the clustering and partitioning centralities on that. Okay, okay. Now, will any questions or any clarification? As I told, this is a very big topic on that, which I used to take for undergraduate, postgraduate, PhD things and different levels and different hands on. Okay.